This is Geometry Unit 8, Lesson 1 on similarity. When we're doing similarity, what we're going to be looking at are figures that are similar to each other instead of just congruent. So let's review how we know things are congruent first. Well, let's talk about rigid motions. A rigid motion or an isometry is a composition of transformations that preserves distance. Now, we talked about these when we did transformations. The basic rigid motions, the ones that preserve distance, are reflections, rotations, and translations. All three of those preserve distance. So they are called rigid motions or isometries. Now they also, besides preserving distance, they also preserve angle measure. Because remember, when you do a rigid motion, what you start with is what you end with. So your figure will always be congruent to its image when you do a rigid motion. So congruent means two figures are congruent if one is the image of the other after rigid motion. If you do one of these transformations or some combination of them, the two figures that you start with, one you start with and its image that you finish with, will be congruent. So let's describe a sequence of basic rigid motions that could show that triangle ant, which would be ANT, this triangle, is congruent to triangle bug, BUG. So remember, there's more than one way of doing it, so this is just one sample way of doing it. So we are going to do a combination of a translation, a rotation, and a reflection. So let's see what we do. We're going to translate. Remember, translate is a slide. So I'm going to translate, I'm going to take this triangle and I'm going to slide it up to the dotted triangle along vector TG, like so. So I'm going to translate along vector TG. Now, when I go from T to G, that means that when I'm done, point T will align with point G. So this is now my new point of my triangle, and I have the triangle A prime, N prime, G prime, or G, A prime, N prime, G, because T becomes G. So now I want to take this dotted triangle and I want to rotate it. Now remember, rotation is always defined as either clockwise or counterclockwise. So I'm going to go over here, so I'm going to rotate this direction. So I'm going to rotate clockwise until I want to get A prime G coinciding with G, or BG prime, or BG prime. Yeah, I said that wrong, BG, sorry about that. Okay, so we're going to rotate until this side ends up here on that segment. So that's going to be my rotation. So this triangle will turn like this to end up like this. So now my new triangle is going to be B, G, and double prime. Now notice here, A prime ends up at B. So we have A to A prime to B, so we have A prime becomes B. Now, the last thing we want to do is we want to get these to coincide. We already have A corresponding to something, we have T corresponding to something, so we need N too. So N becomes N prime, then becomes N double prime, and then you do a reflection over BG, and that gives me N prime becomes U. So are these two triangles congruent? Yes. As long as A prime becomes B, N prime becomes U, and T becomes G, these triangles will be congruent. If any points don't line up, the triangles will not be congruent. So if any points don't line up, the triangles will not be congruent. Now, congruence is nicely defined in terms of rigid motions, but rigid motions are not a convenient method to actually decide if two figures are really congruent. How do we really know that those points line up to each other? So for triangles, we actually developed some congruence theorems. We just finished a whole unit on this. We have 5 ways of proving triangles congruent. We have side angle side, two sides angle between them, angle side angle, two angles in the side between them, side side side, all 3 sides congruent, angle angle side, 2 angles in the another side not congruent, and for right triangles, hypotenuse leg. So using these 5 basic congruence theorems, we can prove triangles congruent for certain. Now, what we're going to be working on is proving that triangles are similar, not congruent. So we're going to be looking at similarity transformations. A similarity transformation is a composition of transformation that scales all distances by the same ratio. Okay, so that means that instead of coming out with a figure that's congruent to its image, it's going to be a different size. So that means that you are going to multiply each side by the same number. A ratio means you multiply. So you're going to multiply each side by the same factor. Now, it may be a whole number, it may be a fraction, so you have to know what you are multiplying each side, but it's exactly the same every single time. All right, so if we have triangle ABC, where AB is 12 and BC is 18, and we do some transformation on it to become A prime, B prime, C prime, how do we know if it's a similarity transformation? Well, we want to look at how the corresponding sides are in the same ratio or not. So let me sketch myself a triangle here. Here's triangle ABC. And I have on triangle ABC that AB is 12 and BC is 18. Now, I'm going to do a transformation where A prime, B prime is 18. All right, so I'm going to actually have a bigger triangle. I don't know how big, but it's going to look something like this. All right, and then I have A prime, B prime, C prime. So A prime, B prime is 18. And B prime, C prime is 24. Obviously, this is not to scale. All right, is T a similarity transformation? So what we're going to do is we are going to compare this triangle side to this triangle side and see if the sides are in the same ratio. All right, so what did we multiply to get these? Well, let's divide to figure out. We're going to do the ratio of A prime, B prime compared to AB. A prime, B prime is 18. AB is 12. If I divide this out, I get 3 over 2 or 1.5. Okay, now if this is a similarity transformation, if I do B prime, C prime the same way as I did AB, it should be the same. Let's see if it is. B prime, C prime over BC, image over starting. So the image is 24, the starting is 18. 24 divided by 18 is 4 over 3, or 1.33. So, is this a similarity transformation? No, it is not. These are not the same ratio. The sides are not what's called in proportion. So, these two triangles are not a similarity ratio. Okay, now, what if we did a different transformation? Let's do it the same way, except this time we're going to change the values of A prime, B prime. So, if we do A prime, B prime this time compared to A, B, A prime, B prime this time is 8, and the original AB was 12. That reduces to 2 over 3. Compare B prime, C prime to BC. B prime, C prime is 12, and BC was 18, and I reduced that 2 over 3. So is this a similarity transformation? Yes, because the sides are in proportion. They have the same ratio. So when they're in proportion, that means they have the same ratio. So when you have similar triangles, all of the sides must be in the same ratio. They must be multiplied by the same thing every time. So which of the basic transformations that we learned are similarity transformations? Well, the only transformation that we multiply on is a dilation. A dilation is multiplying. So D of K is a similarity transformation with a ratio of, remember, that is your ratio or your factor. That's what you're going to multiply the terms by. So your sides will be in the ratio of whatever K is to 1. So if you're doing a dilation of 3, this would be a 3 to 1 ratio. All right, what you end up with is 3 times as big as what you started with. So that is your ratio. Now, all rigid motions, reflections, rotations, and translations, are technically similarities too. Now, because what you start with is what you end with, what is your ratio of the sides? Well, it's actually going to be 1 to 1 because they're going to be the same every time. So what you start with is what you end with. So the only new one we're talking about is the dilation because it changes the side. It's going to change the size of the figure. Now, so the major properties of similarity transformations, distances are all changed by the same ratio or by the same factor. You're multiplying them by something. But is angle measure changed? No, angle measure is preserved. You have the same shape, just as a different size. So all the angles will still be congruent, no matter what, if you're doing a similarity transformation. So let's look at a similarity transformation here. Two figures are similar. The symbol for similar is just the little tilde symbol. It has no equal sign. If one is the image of the other after similarity transformation. So the only difference with a similarity transformation is you're going to have to do some kind of dilation. And a dilation is done so that you can match the sides. So the first thing I'm going to do is the dilation. Now, when you do a dilation, you have to have a center of dilation and describe what the factor is that you're going to multiply it by. So I'm going to look at my dilation here. I have a smaller triangle, and I want to end up being a bigger triangle. Cat becomes dog. So C is going to be D, A is going to be O, and T is going to be G. Now, how am I going to dilate this? Well, I have to tell my center of dilation. I want AC to be big enough to become OD, or AT become OG, or TC to become GD. So we are actually going to have to make this bigger. Now, my center of dilation, the common point, is going to be at A. So my center of dilation is going to be A. Dilate at center of A by a factor. Well, if I have AT, I want it to be AT prime. So my dilation factor is going to be a ratio of R equals, what you end up with is, technically would be over here OG, this side right here. I want it to be that length, OG, compared to AT. I want it to end up this length when starting out this length. So that's going to be my factor, whatever that factor that might have to be. So that's going to make A into AT prime. AT into AT prime, excuse me. Now, then I'm going to translate. So I'm going to go along vector AO. So I'm going to go from here, the big triangle, the dotted triangle becomes AO right here, so A becomes O. There's my first point that lines up. Then I'm going to rotate. Well, how could I get these to line up? If I could get this to line up, all I have to do is rotate this clockwise until OT prime, T double prime, I'll put it that way, this side right here, will coincide with OG. Okay, so this side ends up like this. So this is going to turn like this until this ends up here. So, are these two triangles similar? Yes, they are. If we know that A ends up at O no matter what, then we would want T double prime, this point right here, to end up at G, and C double prime, which would be this one right here, ends up at D. If any of these don't happen, then the triangles are not similar. So the properties of similar polygons that you need to know. All pairs of corresponding or matching angles are congruent. The angles have to match. But all pairs of corresponding or matching sides are in proportion. Now remember that means has the same ratio. So the words in proportion means in the same ratio. So, just like for congruent polygons, similarity statements are written so the corresponding vertices are in the same order. So that means if ABCD is similar to PQRS, that means that angle A will be congruent to angle P. Angle B will be congruent to angle Q. Angle C will be congruent to angle R. And angle D will be congruent to angle S. Now the sides also have to be in proportion. We'll talk about those in the next lesson.